We looked at some simple circuits. In Chapter 23, we're going to look at some more complex circuits. And to do that, we're going to have a more robust set of rules for analyzing circuits. And we'll take a look at those in turn. Now first is one you first saw in Chapter 22. It's called Kirchhoff's junction law. And I want you to think about this. I've got these two resistors that are hooked up in a circuit. And you look at this on the table, and you see this jumble of wires, okay? This is kind of hard to interpret, but we can make a diagram of this circuit. And we'll make a diagram using symbolic elements, and it's easier to figure out what's happening. I've got a power supply connected to two resistors, okay? And these are big resistors so that you can physically see them on the table. This is the nest of wires. Next to it, we have the diagram to help you understand what's happening. But now what I'm going to do is this. I'm going to break the circuit, and I'm going to measure the current that goes through just this resistor. Just this resistor. And if I do that, what I get is 1 milliamp. I get exactly 1 milliamp through this resistor right here. Now, I'm going to hook up my meter so I measure the current in this resistor. And if I do that, what I get is 10 milliamps. So 1 milliamp through this resistor, 10 milliamps through this resistor. This wire supplies the junction that goes to both these resistors, as you can see by looking at the circuit diagram. So here's a question for you. 1 milliamp goes here, 10 milliamp goes here. How much current is in this wire? How much current comes into this junction in the circuit? We'll give you some choices. And in fact, you'd be able to guess the answer even if you've never seen this. There's 1 milliamp that goes into here. There's 10 milliamps that goes into here. There's a total of 11 milliamps that comes out of the junction. How much current goes into the junction? Let's go ahead and measure and see. But I think we know what the answer is going to be. Here's the current that comes out of the power supply into that junction. We'll hook it up, and what we measure is 11 milliamps. So 11 milliamps comes in, 1 milliamp and 10 milliamps or 11 milliamps goes out. And so the current that comes into the junction is the same as the current that goes out. That's Kirchhoff's junction law. Now this isn't a new law of nature. This is conservation of charge. Current is the flow of charge. Any charge that flows into the junction has to flow out. Charge can't be created. Charge can't be destroyed. But now I'm going to rebuild this circuit, and we're going to look at not current, but voltage, and look at another rule for analyzing circuits. And I'm going to hook them up in a different way. I'm going to hook them up one after the other. So what's going to happen is this. The power supply is going to be connected to this resistor. This resistor is connected to the second resistor. This one is connected back to the power supply. And instead of having 10 volts, I'm going to increase the voltage so that it's 11 volts. So 11 volts, I've got a resistor here, and I have a resistor here. They're connected up in turn, making a single loop, okay? And the diagram makes that clear. Now, I want to measure the voltage across this resistor. Okay, it's 11 volts from the power supply. This resistor, if I measure the voltage across it, and I can do that by taking my meter and setting it to measure volts, this resistor has a voltage of 10 volts across it. Okay, so the voltage drop from here to here is 10 volts. 11 volts from the power supply, 10 volts here. Question, what is the voltage across this resistor? We'll give you some choices. I bet you could have guessed this. There's 11 volts out of the power supply. There's 10 volts across this resistor. How much is across this resistor? Well, let's hook up a meter and verify what we know the answer is going to be. The voltage that we measure across this resistor right here is 1 volt. There's 1 volt across this resistor. Because the voltage goes up by 11 volts in the power supply, it drops by 10 volts here, it better drop by 1 volt here. Because the voltage has to end up basically back where it started from. If you go around the loop, The increases in voltage and the decreases in voltage as you go around the loop have to sum to 0. And this isn't a new law of nature. This is conservation of energy. Voltage is potential. Potential is related to potential energy. And if you start at a certain potential energy, you better finish at that potential energy. So if I start at 0, go up to 11, drop to 1, I better drop 1 more volt to end up back at 0. And this is called Kirchhoff's loop law, and it's the second tool that we have to analyze circuits. Now, in fact, this is a pretty straightforward circuit, but in the chapter, we'll see circuits that are more complex that this law will help us analyze. And we'll do that in the next segment.